Hello ladies and gentlemen, we are Get On Board, getting you on board, on time. My name is Jeff Khvu.
My name is Nikhita Singh.
My name is Zachary Mulder.
My name is Christopher Rao.
And my name is Winne Yan. So before we give you a run through of our simulation, we wanted to give you a little bit of background on why we chose to create a passenger boarding simulator. So as of 2008, there are approximately 93,000 commercial flights that take off from airports every day. For the portion of domestic flights within that 93,000, there is on average 140 passengers per flight. As airlines implement new policies such as checked baggage fees, more and more passengers are opting to bring carry-on luggage. And factors like this have resulted in airlines needing 30 to 40 minutes in order to board all of their passengers for a single flight. This increase in boarding time has led to an increased chance of a flight being delayed. And the longer wait time for customers means that there's going to be more frustration and a lower overall satisfaction with the flight and with the airline itself. So currently, our market consists of approximately 240 airlines worldwide, which each implement a couple different methods for boarding their passengers. There's open boarding, where passengers are not assigned seats but are boarded based on their check-in times. There's rear to front boarding, where passengers that have seats near the back of the plane are boarded first. There's also zone boarding, where sections of the plane are assigned to a specific zone, and passengers within those zones are boarded together. Finally, there's outside-in boarding, where passengers with window seats are boarded first, followed by those with middle seats, and finally those with aisle seats. So, airlines already know that boarding times are a major bottleneck in their departure process. And while some research has been done on this issue, there is still a lot of room for improvement. With over 93,000 flights taking off every day, efficiency improvements could lead to a sizable reduction in the costs associated with an airline's boarding process, and an increase in the airline's overall bottom line. For these reasons, we believe that there is a large market that would be interested in a useful solution to their boarding problem, and that's where our product comes in.
Get On Board is a highly customizable tool that allows airlines to test and identify optimal boarding strategies suited for their company. At its core concept, Get On Board allows users to input a variety of parameters to create a robust boarding simulation. Once these parameters are entered, the simulation begins. Passengers move down to their assigned rows, they store their luggage, and then they sit down in their seats. Here's Zach with a quick demonstration of how that works.
So let's say we're at the beginning of a boarding process and the first customer clears the gate. That customer, let's say, is assigned the 5th row. They will then go down the boarding ramp into the initial queue at the front of the aircraft. At this point, they'll see that there's nobody in front of them in front of the central aisle. Thus, they'll continue to walk down the aisle until they reach their designated row. Let's say at the same time, another customer enters the boarding ramp who is assigned to the 4th row. They will go down to the front of the aircraft, and since neither of them are blocked in front of them, they will continue moving down the center aisle until they reach their designated seat. Now, once they reach their designated row, a customer will start to load their luggage into the overhead bin, while the other customer will continue moving forward until they reach their designated row. Once this starts to occur, the customers won't be able to sit until they finish loading their luggage. So let's say while they're loading their luggage, another customer arrives who is in the 5th row. A customer will go down the boarding ramp into the initial queue, and since nobody's in front of them in the central aisle, they will continue walking down the central aisle until they reach the 3rd queue. At this point, they can't move any further because they are waiting for the customers in the 4th and the 5th queue to finish stowing their luggage. Once those customers finish stowing their luggage, they'll take a seat, and this customer will be able to continue down to his assigned row, where he will then start to stow his baggage, and then he will finally take his seat. This core component captures much of the boarding process. However, there are 2 other subtle events that can lead to drastic differences in overall boarding time.
Since passengers can arrive in random order, it's possible for a passenger with a window seat to arrive at his assigned row and find someone sitting in the aisle or middle seat. Have to wait for that person to get out of the seat and move into the aisle before being able to go and sit in that seat. This effectively adds time to the overall boarding process. Another feature we wanted to include was allowing groups sitting in the same row to be able to board together. These groups would be things like families or couples or groups of friends. We feel like they should be able to board at the same time as well as sit and enter their rows at the same time. And here's Zach with a quick demonstration of how that works.
So let's say we have a group of 2 who are both assigned to the 3rd row. Now obviously the first customer down the center aisle will start to load their baggage. However, since the overhead luggage area is a little bit bigger than the rows, we think that the second person should also be allowed to concurrently stow their baggage. Thus, both of these people will start to stow their luggage, and when they both finish, they will efficiently enter the aisle. That means that they'll enter the aisle so that they don't have to get back up again. So this means that, say, this first customer will sit down in the window seat, while the second one will sit down in the middle seat. This leads to a time savings, as customers who are not independent are not treated independently. Thus, we have created a product that is very customizable and accurately captures the boarding process without being overly detailed. To give you a little bit more about the customizability, I'll pass it along to Chris, who will tell you about the product features.
Get On Board has a number of customizable parameters to model different boarding styles through a user-friendly interface. These parameters are such as the number of seats in a row, the number of rows in the plane, the number of boarding groups, and their sizes. Our product also has the option to load passengers from front to rear or rear to front, and the ability to adjust the ratio of passengers with no carry-on luggage and the ratio of passengers in a boarding group there are in a group of 2 or 3 people. With this flexibility, we are able to perform sensitivity analysis for a given set of parameters to obtain an optimal boarding style. Given these product features, here are some of the objectives we have achieved. Our product allows airlines to test multiple boarding models and to test different scenarios. With that, they are able to identify the optimal boarding method for airplanes of different sizes. They also have the ability to test the effects of policy changes, such as removing checked luggage fees from passengers, to see the effect on overall boarding times. Now that you have the features and objectives, I want to pass it back to Zach for a demonstration of our product.
As the user opens our product, they're greeted with a splash page that gives them 2 options. 1, to set up the experiment, or 2, to run the simulation. Let's look at setup experiment. As you can see, there are a lot of different input parameters that can be altered. We decided to design our project with this in mind to allow the customer, who we assume to be an experienced operations researcher, a lot of control over the experiment because they understand what is going on underneath the hood. With that in mind, let's take a look at some of the details. First, in the experiment section, we have the number of seats in a row, the number of rows in the plane, and the number of boarding groups are some of the more important data points to enter. From there, the user can specify extra data about each boarding group. They can go in and specify the first row and the last row in each boarding group, as well as the ratio of customers with baggage and the ratio of customers that are in groups of 3 and in groups of 2. From there, let's take a look at the timing data. Now, each input in the timing data specifies a beta distribution for the timing input. We chose to use beta distributions because we figured that allowed the user the most level of customizability over each distribution. So a beta distribution follows a min and a max, and it uses a shape parameter P and Q to determine what kind of distribution it is. So let's just go down the list and look at what each of the different timing inputs actually is. So first is the inter-arrival time, which is the time it takes the customer to move from the gate down the boarding ramp. Next, we have the time to load baggage, which is how long it takes the customer to load their baggage into the overhead bin. Next is the time to sit, so how long it takes the customer to enter the row and sit down. Next is the time to wait for seated people, which is how long it takes for customers to stand back up if someone needs to pass. Next is the time between boarding groups, which is the time it takes them at the gate to switch between boarding groups. And last is actually a constant, which is the time to move. Also, you can also edit the experiments and timing data using this pop-up. What this pop-up allows you to do is it allows you to add extra experiments to the run, and it also gives you an idea of what the shape of each beta distribution will look like. It allows you to edit your input parameters in the pop-up before you hit close, and next you hit run simulation, followed by simulate, a pop-up that says yes, and you will begin your actual simulation. Once the simulation ends, the user will receive a pop-up notifying them of the end of the experiment. From there, the user selects OK, and a series of pop-ups will allow them to look at the results of each of the individual runs. So clicking on run number 1, we're given this output graph, which gives us all the information of the output trace from the initial run. The information that's contained here is first Q0. Now, Q0 represents the Q at the beginning of the plane, and what you're looking for in the output is large jumps where the initial Q becomes the bottleneck in the system. Next, you can see TI bar, which is the total average time that it takes for each customer to board the aircraft and initially sit down. Next is TF bar, which is the average time it takes for the customer to enter the plane until the time that they finally sit down. And last is S bar, which is the average number of times that a customer must get up to allow other people to enter their row. However, the main crux of the experiment is the total time to board the aircraft, which you can see in the upper right-hand corner in seconds and minutes. So now that you've seen an overview of our product, I'll pass it back to Nikhita, who will give you some of the results of the experiments we were able to perform.
Some of the high-level results we found were as follows. Firstly, larger boarding groups, so fewer boarding groups overall, resulted in much faster boarding times. This makes sense as the probability of waiting to move down the center aisle is much smaller when there's more people within a boarding group. Secondly, boarding rear to front is far more optimal. This is somewhat intuitive as it's far more efficient to push people as far back into the plane before you board the front. Another interesting finding was that boarding groups with higher ratios of 2 or 3 people are faster than groups consisting of mostly individual flyers. Finally, we did some sensitivity analysis on a wide range of parameters and found that the time to board was very sensitive to changes in baggage loading time versus it wasn't as sensitive to other parameters that we studied. The key benefits of our product are that it allows airlines to minimize delays and have more on-time flights. This can lead to increased profits and a better and more optimal use of resources. Ultimately, this achieves much better customer satisfaction, which can be a very strong asset in the competitive airline industry. If you'd like more information, feel free to contact any of us at the emails listed on the slide above. Also, we can be contacted at getonboard131@gmail.com, and we look forward to hearing from you.